Here in exercise 6, we will implement the LDA, so the linear discriminant analysis by computing covariance matrices within class and the covariance matrices of the between class sample means. Now, I described this procedure and the idea behind this procedure, so the math underlying or that justifies this approach earlier in the book chapter. So I'm not going to take the time to explain it now. But basically, we get these two covariance matrices within class and between class. And then with these two covariance matrices, we perform a generalized eigendecomposition. And from this generalized eigendecomposition, we get the two generalized eigenvalues and the eigenvectors. And then we want to project the data. So the data from data space, we project them into the LDA space, or it's also called the GED for generalized eigendecomposition space, because the classification works by determining whether each data point, each data sample has a negative or positive projection onto the first component. Okay, and then you can generate this figure 6. So let me show you what this figure looks like. Okay, so it starts off kind of similar to the visualization we made in the previous exercise 5, although it is a little bit different, slightly less fancy, because I didn't use Seaborn to create this plot. So here we see all the data points for the two different classes. You can see that they are separable using a line here. So if we would draw a straight line here, we would accurately classify most of the data points. So this is the data in the original data space. These are the data in the generalized eigendecomposition space, also called LDA space. And here we just want to see whether we project the data negatively onto the first axis or positively onto the first axis. Now you can also see that all of the data together pooled have a mean of 0. So the mean on this axis is 0 and the mean on this axis is 0. And that is why the mean centering to create that, what I call variable x tilde, is important, because when the data are mean centered and then projected onto this generalized eigendecomposition space, then classification is as simple as determining whether the value is negative or positive on the component with the largest eigenvalue. Okay, so then you can compute this. So here we have the predicted class based on that projection onto the first axis. And here's the sample number. Now we know, based on how we simulated the data, that all of these points, the first 200 points, should be class 0, and the second 200 points should be class 1. So all of these points here are mistakes. These are misclassifications. These are also misclassifications. But overall, we do really well, right? This is extremely high accuracy. We predict 96.25% accurate. I would say that is quite high accuracy for, a problem like this, where you can see the data points are overlapping, right? So there's blue circles here clearly in the middle of the cloud of red plus signs, and there's red plus signs here. So it cannot possibly be perfectly separable. But for, the generalized eigendecomposition, the LDA does really well. Okay, so that is the goal. This is a pretty challenging exercise, so take a deep breath. Feel free to consult back to the chapter, and also feel free to peek at my solution code. And I hope you enjoy working through this. Quite a challenge, but I think you can do it. And now I will switch to Python and show you my solution. Let me actually start with the within class covariances, because I think that is conceptually and also computationally very simple. So basically, we take the covariance matrix of class 1 and the covariance matrix of the data for class 2, and then we just average them together. So this is the average covariance within each of the categories. Now, the covariance between the class or between the categories is a little bit more difficult. Conceptually, it's a little bit more difficult. If you have taken a statistics course before and you're familiar with ANOVAs, then you might recognize this kind of between class covariance idea. So it's not implemented in the same way as an ANOVA, but conceptually it's similar to the between groups sum of squares, or the between groups mean square. Okay, so the idea is that we are not considering the individual data points. So we're not looking at the data values themselves. Instead, we just want to extract the means, the averages within each class or within each group. And then we say, well, we don't care about the individual variability within a group. That's here. We're going to consider that like error variance. Instead, we just want the averages within each group, and then we put that together into a data set, and we take the covariance of that data set. So we're creating a data set of sampled means. These are characteristics of the data set where we no longer have access to the original data points. And then we take the covariance of that. So the idea is that this is the distance that we want to maximize, and this is the distance that we are computing relative to. So we want to minimize this variance and maximize this variance. And then we want to find an eigenvector that gives us that solves that problem for us. And, I went through the math in the book chapter, and basically the solution turns out to be a generalized eigendecomposition on these two matrices. So the between class covariance is kind of like the numerator, so to speak. It's not formally a ratio, but kind of like the numerator of the generalized eigendecomposition equation. And this is kind of like the denominator. Okay, once we get this, so, there's a conceptual component to working through why this is the right thing to do and why generalized eigendecomposition is the right solution. Once you get to here, I think the rest of it is relatively straightforward. So we again sort the solutions so that we know which is the largest component and which is the smallest component. And then here I project the data onto the LDA space, or sometimes called the GED space. And you can see, as I mentioned, it's important to mean center these data, and then we just multiply by the eigenvectors. Okay, so run that code. And then, everything else, I think I'll run this code to produce this visualization. Of course, I encourage you to go through this and look at all the code and see how I've implemented it. I don't think this is terribly, there's nothing like really core to linear algebra about this code. This is just basic matplotlib data visualizations. Okay, so I do want to talk more about this, in particular, this line of code here. So here I'm saying the projection onto the first axis of the generalized eigendecomposition. So this is the first component. And is that greater than 0 or less than 0? Now, this on its own returns a Boolean vector. These are all trues and falses. But to make things simpler, for example, with averaging, I want to convert this into numbers, into integers. And you can actually do that in Python just by adding +0. So numerically, this does nothing, of course, but it converts a Boolean vector into a numeric vector. So that's why I have this +0 here. Okay, and then the total prediction accuracy is just whether the predicted labels equal the true labels, and then I take the average of this, multiply by 100 to get to %, and that's it. So here we find 96.75% accuracy. That's really great. We see there's a few misclassifications here, a few misclassifications here, but overall it did really well. Okay, and then here is the other fancy plot that generates the rest of figure 2. Now, what's interesting here is that you can see that when you project the data onto axis 1, that you get a really nice separation between these two distributions. It's not a perfect separation. There's some overlap here. And this overlap is why we are getting these errors. So we get a couple of errors here and here, and basically all of those data points are in here. So it's just not possible to perfectly accurately categorize these data points because, some data point here, you don't know which of these distributions to assign them to. And it's also interesting to see that, the projection onto axis 2 is useless, right? It's totally devoid of information. This axis is completely non-discriminative. We have no idea which data point, which observation corresponds to which category or which class if we would only project onto axis 2.